Okay, I think we'll make a start. Hopefully everybody can hear me. Charlotte, if you can put something in the chat if the audio is okay, please. Thank you. Great, fantastic. Thank you, Angus. Thank you, Charlotte. Fantastic. Okay, so hello, everybody. Good afternoon, and it is my pleasure to welcome you to this REDAWN webinar series. This is the second series we're going to hold this year, the first set in the summer, and now in the autumn, we're hosting a three-part webinar series on reducing energy dependency in Atlantic area water networks. Ultimately, the webinars will be talking about micro hydropower and how they are implemented in water networks for various benefits, including conserving energy, recovering energy, and improving the sustainability of water processes. So I am Kemi Adieye. Charlotte and I are based at the University of Bath. I should say that the webinar for this week is pre-recorded for a number of reasons, one of which is to help us have a seamless webinar without technical glitches. However, we'll be having a live question and answer session where our experts are going to be taking and responding to your questions. So please use the chat functions, or when the time comes, raise your hand and we'll bring you into the conversation. I think Charlotte also said in the chat that the webinars are being recorded, so please bear that in mind when you're participating, that we are recording this webinar and it will be available on YouTube, on our YouTube channel after this. Okay, so I will turn off my video to save on bandwidth, and I'll turn it back on when we get to the discussion session. This webinar series is organised and hosted by the Reducing Energy Dependency in Atlantic Area Water Networks, the REDAWN project. The project is part-funded by the Interreg Atlantic Area Programme through the European Regional Development Fund. The map of countries and regions covered by this funding programme are as shown. The project is being delivered by a consortium of 15 partners and valued associate partners from 5 countries along the EU Atlantic area coast. And of course, our partner in Italy, a leading expert in micro hydropower, who will be delivering the first of today's talk. The world's energy use is forecast to increase by approximately 50% in the next 30 years. Our current energy sources are dependent on fossil fuels. This is unsustainable, and the associated climate change impacts are significant. Therefore, fossil fuels cannot continue to dominate our energy provision into the future. For this reason, the EU's 2030 vision aims to significantly increase the uptake of renewable energy technologies, setting a 45% target for renewable energy production and a 40% reduction of greenhouse gas emissions. The total length of the drinking water network in Europe is more than 4 million kilometers, which is 11 times the distance from the Earth to the Moon. This vast network in the EU supplies a total volume of 44.7 billion cubic meters of water per annum. Imagine the significant amount of energy recovery potential in the network that brings water to our taps, not considering the potential in wastewater and other networks. Therefore, we cannot dispute that hydropower is a widely available form of renewable energy that can help to reduce the reliance on fossil fuels for the abstraction, treatment, and distribution of our water. It offers a more sustainable, non-disruptive, and economically viable solution. For this reason, we're pleased that you can join us today to explore this energy recovery potential in water and wastewater systems, irrigation, and industry networks, The focus of our work is on micro hydropower. Micro hydropower refers to a type of hydropower that produces from 5 kilowatts to 100 kilowatts of electricity from the natural flow of water. Our studies have shown that about 650 gigawatt hour per year can be derived from water networks in the UK, Ireland, Spain, France, and Portugal alone. As you will hear shortly, micro hydropower offer benefits beyond energy recovery. Across Europe, about 23% of water losses occur in networks. This equates to around 2,171 cubic meter per kilometer per annum. The appropriate design and location of micro hydropower and ancillary devices can help to achieve other network management benefits, including pressure and leakage management. Micro hydropower also offers all stakeholders the opportunity to innovate and do things differently. Climate change and other resource factors mean that there are water, energy-related risks that need to be addressed in the water sector. These risks have associated financial impact. Exploring and implementing renewable energy solutions, including micro hydropower, goes a long way in mitigating the environmental, social, economic risks associated with our water systems and processes. So, today's seminar will focus on the state-of-the-art in water networks and highlight the energy-saving potential in such systems. The first talk will present an overview of the latest micro hydropower technology, pump-as turbines, highlighting its technical and economic advantage over traditional systems. The second talk will present a case study where this system has been implemented, demonstrating that this approach also works in practice. So it's my pleasure to now introduce our two speakers and expert panelists for today. Our first speaker is Professor Armando Caravetta. He is a full professor in hydraulics at Federico II University in Naples, Italy. He is a renowned expert in pumping systems, efficiency, and energy production in water networks. He is also a member of the working group of the European pump manufacturers for the development of the EC standards for wastewater pumps. Our second speaker is Dr. Miguel Crespo. Miguel was a researcher at Trinity College Dublin. He is an expert in energy recovery and efficiency in irrigation networks using micro hydropower solutions. He is also a shareholder of a TCD spin-off, Easy Hydro Solutions Limited. For today's webinar, I'm also pleased to welcome Dr. Oreste Feccarotta to the discussion panel. Oreste is Assistant Professor tenure track in hydraulics at the Department of Civil, Architectural and Environmental Engineering of the University of Naples Federico II. His research field is mainly focused on the energy recovery and efficiency of water supply and distribution systems. He has developed some research studies on hydraulic structures and on the rheology of non-Newtonian fluid sediment mixtures. He is also responsible for the equipment and lab technicians of the Hydro Energy Laboratory at the University of Naples. Thank you, everybody, and now we'll start with the presentations. So now for the first presentation.
Welcome to everybody. My name is Armando Carravetta, and my contribution to the REDAWN webinar of today concerns the opportunities for energy recovery with the latest pump-as turbine technology. The concept of hydropower pressure reduction comes out from circular economy. That is a modern methodology for a sustainable growth of complex systems. We know that the geometry of water networks was not changed so much from the historical era to the modern age. if we consider the Roman pipelines and the Roman aqueducts were not so different from the aqueduct and the pipeline system of today. Water was kept from the spring and with the long channel was transferred to the urban centers, the Roman centers. And in the Roman village, there was a distribution similar to the present distribution with pressurized systems. Of course, water treatment is a concept of today, and also the possibility of a reuse of the water for different scopes. But this concept of reuse of water and of the resource is very limited, and in particular, the water that we obtain from treatment plant has a very small pressure head compared to the pressure head of the water to the source. So it is water that, from the point of view of the concentration of chemicals and of the properties, could be good for irrigation or could be good for industry, but as a small hydraulic power. So, how can we consider that the water network is consistent with circular economy concept? In the circular economy concept, we imagine that in all phases of the process, we can recover and save our resources. The possibility for recovering resources in water networks comes out from the fact that the water networks are very energy-consuming systems. And a large effort were made by the European community to improve this efficiency. This concept of low efficiency is connected with a large amount of water that is lost in leakage that could arrive to the 40–50% of the water at the spring. Where is used the energy? Energy used in pumping for water transportation from one point to another of the network to overcome high point of elevation. Energy is dissipated to optimize the pressure because downhill we need to reduce the pressure in order to obtain an optimal value for the end users. Energy used in pumping for urban drainage, so in the drainage network, and it is used in all phases of the treatment process. The treatment process is very energy consuming, and most of the energy used in water networks is used in the treatment during the treatment process. The European Community already implemented the circular economy contents by eco-design. In this case, the European Community imposes to use this concept of circular economy by product innovation. So, eco-design is the idea of producing better product for better devices, in particular pumps for the water networks. In this way, much of the energy that you use now will be saved, but not only for the product, also for the integration of the pumps with the motor, with variable speed drive, and the integration of this group of pump, motor, variable speed drive within the system, the pumping system. The idea of eco-design is that it's hard to obtain savings from a process innovation because water networks are traditionally adequately managed. So, in the meanwhile, we push for an energy control of this network with new standards. But if we cannot use circular economy cannot come these savings from a process innovation, they can come from product innovation. So pumps and motors, as I told, are under the eco-design umbrella, and a new minimum efficiency index was introduced for pumps, an extended product approach for pumping group, so the pumps integrated with the motor and integrated with the variable speed drive, and the dynamic control of pumping system. That means that we have to check with energy auditing that the correct group is used for the system where it is planned. So with this energy audit, we have to check that all pumping systems at the moment are used properly. We can suggest to change some pumping groups that are not enough efficient, and we can check periodically that the new group are well integrated in the system. Unfortunately, much of the energy stored in the system is simply lost. A large amount of water is lost in the joint and is lost in the breaks of the pipes because of the pipe age. And in this way, when we pump water and a part of this energy is lost because we are pumping much more water than necessary. In the meanwhile, the way to reduce leakage is to reduce the pressure. And this strategy has already been implemented. It means that we have to flatten the pressure in order to have the best pressure in all the network. So, by reducing the pressure, we reduce the leakage, and by reducing the leakage, we reduce also the energy that is used in pumping. The novelty of our proposal is in recovering the energy that now is dissipated in the valves, in the regulation valves, in order to have the pressure containment. Hydropower pressure reduction generation is the way that we propose to recover this energy. We can explain the concept that is on the basis of hydropower pressure reduction by an analogy with F1 cars. The Ferrari 2008 was very different from the Ferrari 2009, not from the aerodynamical point of view, even if some differences are present, but because the brakes that were present in the 2008 were substituted by a new technology that is now still used in the cars, that is the KERS. This KERS is a motor that is coupled with the axis of the car, so when it is necessary to reduce the speed of the car, the motor is in contact with the axis and brakes the car by the resistance of the motor itself. The energy that is produced by the electric motor is stored in a battery. The idea is the same. We can explain the concept that is on the basis of hydropower pressure reduction by an analogy with F1 cars. The Ferrari 2008 was very different from the Ferrari 2009, not from the aerodynamical point of view, even if some differences are present, but because the brakes that were present in the 2008 were substituted by a new technology that is now still used in the cars, that is the KERS. This KERS is a motor that is coupled with the axis of the car, so when it is necessary to reduce the speed of the car, the motor is in contact with the axis and brakes the car by the resistance of the motor itself. The energy that is produced by the electric motor is stored in a battery. The idea is the same that is used in our hydropower pressure reduction technology. So at the moment in the water networks, the energy is dissipated in the valves. So basically in a butterfly valves or in a gate valves or in a pneumatic valve, we have the current faster in the valve and then slow downstream the valve, and this slowing of the currents produce a larger vorticity and a larger dissipation. In this case, we replace the valves with an hydropower plant station, and it is the current pass in the turbine or in the pump's turbine, and there is an exchange of energy between the current and the motor of the turbine or of the pump, and so the energy is reduced. So the concept is the same. Now this energy is stored somewhere else in the electric grid, and the efficiency of the network is boosted like in an F1 car. Why pumped turbine technology is the best technology for hydropower pressure reduction design? Because we have a very limited hydropower size, so the power is generally below 50 kilowatt and can go to 1-2 kilowatt. And pumped turbines are in this case the best generator. The water manager to satisfy the end user. And so they need a very reliable technology. And PAT combine low cost and high reliability. Low cost is necessary because the hydropower site is small and we cannot spend so much in a miniaturized turbine. The reliability is necessary because pumps are very reliable devices, and so a pump used as a turbine. Managers are familiar with pump and will be familiar with pump used as a turbine. So REDAWN looked for guidelines for hydropower design, and these guidelines are necessary to obtain the best location of the hydropower plant in the network, and also because different kinds of hydropower pressure reduction plant are possible depending on site. By implementing guidelines for diffuse hydropower design, we are giving principle of hydropower pressure reduction, the basis for hydropower pressure reduction location, and the tools for hydropower pressure reduction design. Here we see some aspects of hydropower pressure reduction. So we have a location where we install the PAT, and by reducing the pressure, we reduce the pressure in the whole branch of the network downstream the location of the PAT, and we have to look to the pressure in all the nodes, and we have to grant that the pressure in all nodes doesn't fall below the optimal pressure value for the network and for the end users. And so the complexity of the design is in selecting the best point for PAT location or for valve location, and to make a proper design of the hydropower plant, considering that the flow rate is changing, and that when the flow rate is larger during the peak of the usage demand, it is smaller the head that has to be dissipated in order to grant the minimum pressure value downstream the PAT. In the meanwhile, we have to look to the economical aspect, because we have to check if the net pressure value will be positive, and we have to consider in this analysis the cost of the PAT, the cost of the construction site, if we need some waterworks, and of course there is the benefit coming also from the reduction of water use because of the containment of leakage. So in this guideline for hydropower pressure reduction, we look at the daily variability of flow rate and pressure drop, and the variable operating strategy is the proper design technology, the design strategy for facing with this variable working condition. The geometry of the hydropower pressure reduction plant and the PAT selection is based on variable operating strategy. And to use the variable operating strategy, we compiled the database of commercial PAT, and we generated some support tools that make possible to technicians make the design of hydropower pressure reduction plant. Pilot power plants were also realized in the REDAWN project and are the most important results of the project, and demonstrate that hydropower pressure reduction is now a real choice for the water section. Here we see some snapshot of the PAT selection tool that is based on all PAT performance curves that we collected are all commercial PAT. So basically we can select the best PAT given the measures that we have of flow rate and pressure head in the site of PAT location, and then we can ask to the manufacturers to check for the best PAT and to offer the best PAT that was coming from our design tool. But we have to consider that we have this large range from 1 to 50, maximum 100 kilowatt of power. When the power is very small, this means in the peripheral branch of the network, we have to save the cost of waterworks. And so within the project, we also developed a new technology that is a energy booster technology. In this case, we introduce the PAT as submersive pump in the booster. In this case, we have two PAT that can work in parallel and a bypass. And in this energy booster, we can is a miniaturized hydropower pressure reduction plant that can be easily located in an existing manhole by simply drilling a hole in the manhole and introducing the booster without any additional waterworks, without problem of noise, without problem of humidity for the surface motors. So it is a very reliable and I think promising technology for hydropower pressure reduction that can be in the future extended to higher powers. Finally, we are very happy to participate to REDAWN, to this consortium, including university, including technical partners, including water utilities and industries and irrigation association, and of course, in case you want to contact the REDAWN project or contact me, here you have the correct address. Thank you for your attention.
Okay, thank you, Armando. And now for Miguel's presentation.
Hello, everyone. My name is Miguel Crespo, and continuing with the presentation of my colleague Armando, I will talk about the application of micro hydropower and pampas turbine within the irrigation sector, more specifically of its application within the on-demand irrigation networks. As a brief summary, we have here the 4 main points of which we are going to talk about during this presentation. Starting from an introduction in which the main problems, the existing problematic, and a brief overview of the context will be explained. Then we're going to pass to the different solutions that have been already proposed to counteract the trending energy depending increase. Then we're going to pass to the hydropower as a potential measure to counteract this energy dependency. And finally, we are going to how within REDAWN we have demonstrated and validated that pampas turbine could be used to decrease the energy dependency in on-demand irrigation networks. Okay, so we are gonna start talking about the problematic, and let's be focused on the semi-arid and arid regions where the water is really important, but also where irrigation normally has a great weight on the economy, on the national economy. So in these areas, in these regions, it's taking place a modernization process that implies normally the substitution of traditional irrigation hydraulic infrastructures like channels or ditches for pressurized pipe networks. So this process was seeking to improve the water efficiency by decreasing the water consumption. However, a negative effect or impact arose from this process, and is that the energy consumed or due to the irrigation increased dramatically. Here is some number of Spain, where after the modernization process, 21% of the water was saved. However, the energy consumed due to irrigation increased by 657% from 1950 to 2007. This has some negative impact on the farmers and on the irrigation. Due to the increase of the energy consumption, the cost related to irrigation increased, and this has some impact also on the annual yields. But within the irrigation, the emissions also increase, which is also negative. So at the moment, we need to, or the irrigation need to be focused on seeking different solutions to counteract this energy consumption. So different solutions have been already studied, and some of them were related to the network management and exploitation. Another one was seeking to optimize the head required at the pumping station, depending on the consumption points working. And now is trending the use of renewable energies. For everybody to know, on-demand irrigation networks are similar to drinking water networks, to the urban ones. And this is due the continuous availability of water independently on the season of the year. So basically, we have water available 24 hours a day, 365 a year. And this flexibility, so this availability of water, together with the large irrigated areas, makes very likely the existence of excess pressure points. And this pressure normally, this excess pressure is normally controlled or dissipated, installing control valves, either in the middle of the network or at the consumption points to give the right pressure required by the irrigation devices. So one way to decrease this energy dependency is through hydropower energy recovery. Among the different solutions that have been already proposed and studied, we can highlight these four that I already mentioned before: the irrigation sectoring, the critical points identification, the pumping station optimization, and the renewable energies. Irrigation sectoring refers to the grouping of the different hydrants or consumption points with similar pressure requirements. So this seems to be very clear in the figure that we have on the left. So on the one hand, we have the pink area, and on the other one, we have the green one. So basically, we group the irrigation network to irrigates by turn, basically by groups that encompass the hydrants with the similar pressure requirements. These models showed very, very important energy savings of around 30%. However, the main advantage that on-demand irrigation network has is lost, and is that the availability, the continuous availability of water is split into different groups. So farmers need to irrigate whenever they have their turn defined. Critical points detection is another of the solutions that have been already studied to counteract the increase of the energy consumption within the irrigation sector. This solution is focused on the identification and location of unique points with a much greater energy requirement or pressure requirements. And this is due to a great elevation difference between them and the rest of the nodes of the networks, due to a remoteness from the water source, or even to a high head losses for an undersize of the network at these points. They may increase the global energy consumption of the network, provoking some high overpressure in some of the nodes that need to be dissipated for a correct operation of the network. Variable speed drive installed in pumping stations, secondary pumping stations before these unique points, or even pipes replacements are potential solutions to solve these issues. So critical points detection and their potential solutions have shown some energy savings that range between the 10 and 30% of the global energy consumed. Another trending solution is the use of renewable energies. As we said before, the modernization process is taking place in some arid and semi-arid regions, where the annual hours of suns a year is very important. So solar pumping can be proposed, or it has been already proposed and used in some regions to reduce almost completely the energy consumption of another. And this is very useful for small networks or small farms. However, this is very unlikely to happen in large irrigation networks, as we have there are a lot of consumption points, and the water can also be required during the night periods. Also, in this kind of large networks, a significant surface is needed to install the enough number of solar panels to fit the pumping station. The one in the picture is one experimental solar pumping station installed in a roof that supplied the energy required during the whole year to irrigate 13 hectares farm of olive trees. So we can say that this solution is very useful when we have maybe a few of consumption points and also a small irrigated area. And here is where the solution proposed in REDAWN comes, the hydropower energy recovery. So let's start with the figure that we have on the right. Here we have a skeleton of an irrigation network with a lot of branches. And in blue here we have a small surface area. This small surface, this small area is causing effect on the pressure requirements of the whole network. And is, as we can see, when all the nodes, all the consumption point irrigates at the same time, we have many areas showing excess pressure. So this excess pressure needs to be dissipated before the water comes to the ground. So what is the main reason of this to happen? So as the areas irrigated, as I said before, are very extensive, and the uniform of the elevation gradient is not there's no high uniformity on the gradient, on the elevation gradient. This makes almost or unavoidable the excess pressure point. So in this pressure where we have overpressure, the energy might be recovered and used either for local consumption or bring the electricity to the pumping station in those cases in which the distance is not too long, or even the electricity could be brought to remote places with no electricity, with no electric grid. But what is the problem? Another issue that arise in the irrigation networks is the seasonality of the activity. The irrigation period is concentrated in some months of the year, so we need cost-effective technology where the investment can be recovered in a very attractive period of time. So where the technology proposed in REDAWN comes. The pumps as turbines. This is just a regular water pump used in rivers as turbine. Instead of catching the water and expelling from one axis, we take the water from the opposite axis and expel it with a lower pressure from the opposite axis. From the very broad literature review, it can be summarized as SWOT analysis here, in which the strengths, weaknesses, opportunities, and threats are shown. And as a strength, we can see here as pump as turbine is a low-cost technology. When I say low-cost technology, we are saying that potentially it could be around 10% of the cost of traditional turbines. So this is actually a massive, significant money saving. Then they have a very good performance and the best efficiency point. And also, they can be found in the market in a massive way, because pumps are manufactured all around the world, and a lot of points are, a lot of working points are being designed and manufactured. So this can reduce the delivery time for this technology. As weaknesses, we have that out of the best efficiency point, they could show a low relative efficiency. And this is because of the flow fluctuation. So in networks that have significant flow fluctuation, a very careful design needs to be done. Well, the demonstration side. This is the energy recovery at farm level. In this case, instead of going to a large scale, on the REDAWN project, we decided to go to a small scale to provide energy to a farmer. Why this was an attractive solution? Well, on the first on the one hand, we had an hydrant from which the water was taken for the farmer, and was supplied in the irrigated surface close to the hydrant. Then they have also an energy consumption. There was no electric grid. The energy was generated by a diesel generator. So here we had two positive points. We have an excess pressure on the hydrant that was being reduced using pressure reducing valve, and also we had an excess an energy consumption at the farm that was supplied by a diesel generator. And so this, using PATs or energy recovery in on-demand irrigation network, could be also proposed as a potential and attractive solution to bring electricity to remote places. When designing this pilot, well, the first thing that we need to confirm was the existence of excess pressure at the node, at the hydrant, and we can see here how the pressure varied along the month within the irrigation season. Starting in March, we had almost 90 meters of pressure, and then in the most intensive irrigation stage of the season, we had around 55. So normally the pressure required at the hydrant for the right operation of the farm was 35 meters. So we have a minimum of 20 meters of excess pressure that was being dissipated. Also, we had a flow that varied between 0 and 190 liters per second, as the farm was irrigated around 300 hectares of walnuts. And then the energy requirement that we were talking about at the farm was being supplied by a diesel generator, 7 kV. That were this diesel generator were 2 fertilizer pumps of around 2.2 kilowatt total. Then an air compressor of 1.1 kilowatt and a filtering station of around 0.3 kilowatt. So using the input information showed before And keeping in mind that we had at least 20-meter excess pressure during the whole irrigation season, the closest PET or the ideal PET to be installed in this case had a nominal power of 4 kilowatts. And this was installed in a farm located in southern Spain, in Palma del Rio. And the main target was to replace the diesel generator that was being used while the farmer irrigated. The initial scheme of the pilot plant was this. So the PET was installed in a bypass of the main irrigation network. And then to monitorize a little bit the working condition of the PET, we install a flow meter and some sensors to control the pressure and stuff. Then, so this is the existing situation before the installation of the PET. We have here this diesel generator that was feeding this filtering station and some fertilizers over here, and the air compressor used for some maintenance of the farm. Then we pass from this situation around here to this situation in here, in which we have this bypass where the PET was installed and taking advantage of the excess pressure that existed at the farm. Also, we decided to use some batteries as a backup system, just in case that we need to do some maintenance to the PET, or even if there was some lack of pressure, so they never be due to these circumstances. Finally, with the pilot plan, we really validated that the technology could be useful for this kind of infrastructure or to be used within the irrigation networks. And it also validated the idea that we had in the beginning, that it could be used to bring electricity to remote places. So in the first 15 months of operation, the farmers saved more than 3,000 euros and avoid more than 12.8 tons of CO2. But also we need to take into account that in 2020, the cost of the diesel used for the diesel generator drops due to the COVID situation. So we are expecting that in the next few years, this economic savings increase by importantly. And also the payback period, just taking into account this number and the cost of the installation, showed that this kind of solution could be attractive for farmers because they could be recovering in less than 10 years when they have a lifespan of around 25. So I hope that you enjoyed this presentation and overall that you foster hydropower for energy recovery. And thank you very much for your attention.
Okay, we have a couple of minutes, about 9 minutes for questions and answers. So if anybody has any questions, can you raise your hand and then unmute your mic, please? I think we have a question from Paolo. If you can unmute yourself, please.
Yes, I'm activating the camera also. I don't know if you can see. You can hear me?
Sorry. Yeah, we can't hear you. Oreste, can you also unmute yourself, please?
Yeah, I can hear you. Not very well, but I can hear you.
So I'd like to have some information about, for example, the last project that has already been experimented in Spain, of the efficiency of the pipe, but not only the turbine. I would like to see, or you can tell me, the total efficiency of the turbine plus the generator. If you have these numbers.
Okay.
So
I can understand the question. Yeah. Well,
okay.
Of course, it depends. It depends on the manufacturing quality of the pump and of the generator. And presently, the European Union is pushing the market more efficient machines, both motors and pumps. So basically, in the next years, we will see pumps and motors that will be more and more efficient than today. There are a lot of legislation, regulation, and so on about from European Union about that. But the problem is not just the efficiency of turbine motors, because of course the efficiency of the pump as turbines is strongly related to the efficiency of the pump, and the efficiency of the generator is strongly related to the efficiency of the motors, because the manufacturing quality of the motors and on the pumps impacts also on the efficiency of the turbines and of the generator. And I can say the efficiency of the generator can be 90% or more, while the efficiency of the turbine itself can be, of course, depending on the discharge flowing into the turbine, can be also 70 or 80 or 90% for the largest pumps, okay? I can say 70% for a medium size. So 70% of the pumps of the turbines and 90% of the generator can be 65% of both of them. Well, yeah. It's a medium size, but anyway, the problem is in the regulation. I mean, in a water distribution network, the flow in discharge and the available head is not constant. So basically you have to regulate, and if you have to regulate, you lose energy. I mean, for example, the discharge flowing to the turbine is not always the same, can vary during the time. And thus you have different efficiency. If you compare the output power with the all available power, you can obtain reasonably, I say 50% efficiency as the overall data.
You have information about this last project, because, for example, the power of the pet. I have seen two pets, green pets, in this last power plant. You have an idea of the power of these pets? 1 kilowatt, 2 kilowatts, 10 kilowatts?
Well, if I remember, I don't know if Kemi can put the presentation again.
Sorry, what was the question about the parts? I think it was 4.
Yeah, I think it's about the how do you say? Pilot plant.
Yeah, why I'm telling you this? Because we know that when you put a generator, and in general it is an induction generator, majority of the pets. The induction generator, and the induction generator is for powers less than 2 kilowatts. The efficiency, the maximum efficiency that you can put there, and for a normal generator, normal induction generator, it's about 70-75%. I'm not.
Sorry, Paulo, I can hear you very bad.
Let me. I will. Yes.
The audio is not very clear. Sorry.
Yes, I know. I'm sorry. Now you can listen to me now. A little bit better.
A little bit better, yeah.
This is the microphone. You can see.
Okay. Yes.
I can swallow the microphone. Even. Let me do one thing. 4 powers, less than 2-3 kilowatts. The induction generators, the normal induction machines, you have more or less 70%. This is the nominal efficiency. And if you multiply by
in our experience, it can be more.
It depends on the power.
Yeah, of course, but with the IE3 motors,
it can
be high.
But the motors are more expensive. So if the idea is to use the normal pumps operating as turbines and machine from motor to generator, I will not ask for these very expensive and high efficiency machines. These machines are very expensive today yet. So I think the idea of the PET to be low cost will be to use the normal pumps that are sold thousands and thousands and thousands, and take advantage of these low costing pumps and invert the power flow.
I agree with you that it depends on the costs, of course. And anytime you put a modification to earn money, you have to lead how do you say, an economic evaluation of your investment, of course. We did several studies about that. Of course, there is a convenience of investing more money in a high efficiency motor that is more expensive than normal, as you say, but not so much, at least in our experience. But of course, it depends on the available power, on the investment you want to do, of course, but the return of investment, the payback period can be very short. We calculated from 3 to 5 years. So even if you,
okay. Yeah, no, thank you for that. I think the conversation probably needs to continue. But in the interest of time, I think I'll take one more question. Thank you, Paolo. That was very useful.
Thank you.
Joseph is saying, can this technology be used in water well systems, Oreste?
And can you repeat?
Can this technology be used in water well systems?
Okay. Okay. Hi, Joseph. Thank you for your question. Could you please explain what do you mean with water well systems? I assume a well is a point where I can collect water from underground, if I don't.
Yes, I think so. Yes. Yeah.
So what do you mean with this?
Perhaps Joseph wants to unmute himself. I don't know if he's still there.
Okay. Anyway, just to give just
basically, can this technology be used in wells? Yeah. If you have a fixed and you're pumping from a well.
When you have a well, basically you have to pump from the well to the destination point. So basically, the idea is that you don't put more energy than the amount you really need. But of course, this is not possible every time you have a system. For example, like in the example of Miguel or Armando and so on, when you have to pump water from one point to an upper town, an elevated town, maybe some parts of the town are high elevated and some parts of the town are low elevated. So basically, normally you pump at the maximum elevation, and then to deliver water to the lowest part, you put a valve. So basically the idea to using water from wells, and then you pump to elevated town, then before delivering water to the lowest part of the town, you put a pump there. But the best idea is that this is a recovery of energy. This technology is to recover energy. So basically, if you pump water from underground to an elevated point, the best choice you can have is to put the less energy you can in pumping water. So basically, pump the water to the elevation you need. Okay, I don't know if I was clear, but this is my opinion. But Elena probably want to tell something more if I can read the
I think, but Elena, so if you can briefly comment and then we'll finish because we've run over time a little bit. Elena,
Okay.
do you want to add a quick comment?
Can you hear me?
Yeah,
Yes, we can.
Yes, if we have a pumping system, as Oreste explained, in some we can have some pipe branch operating as a gravity systems, okay, connected to this main pumping systems. In this pipe branch, if we have excess of energy, of course, we can implement there a pump as a turbine solution. The resume is more or less like this. I tried to wrote on the chat.
Okay, thank you so much. Okay, I think we'll leave it there for now. I'd like to thank Oreste in particular for answering our technical questions for today, and to Armando and Miguel for their excellent presentations, and also to everybody that attended. I know there's probably other things to do on a Thursday afternoon, so thank you so much for joining us. I've typed an email address into the, sorry, that should say co.uk. I've typed an email address into the chat function. Please continue to send us your questions and we'll try to answer them.
Yeah, Camille, I think that the email address is wrong. It's just with one O before UK.
Yes, so yeah, it should be .co.uk. Sorry, I'll retype that shortly after this. Okay. I should say that this is a series of webinars, so just to remind you that we've got another one next week chaired by Dr. McNabola at the same time next Thursday. Please join us for that, and then there'll be another one the following Thursday after that. So please join us for this webinar series, and think about your questions in advance of them so that we can answer them as well. So that's it from us for today. So like I said, webinar next week, same time, please join us. And also please save the date for the final project event, which will take place next February on 9th of February 2021. Join our mailing list if you'd like to find out more about that, and there'll be more information on the website as well. So enjoy the rest of the day, enjoy the rest of the week, and hope to see you again next week. Thank you so much. Thanks, Oreste.
Thank you, and goodbye to everyone.
Goodbye. Goodbye, everybody.
Bye.